Today we're going to begin our study of chemical equilibrium. First, our challenge is to define equilibrium. Well, what is equilibrium? It's when the rate of the forward is equal to the rate of the reverse. We'll have time to observe a few of these things. First thing we're going to do is look at a reaction between nitrogen dioxide and turning in equilibrium to dinitrogen tetroxide. Now, if one thing I would suggest is on Canvas I've placed a handout. If you want to go ahead and print that, some of these things I say will be on there. I can just point to them in the handout. And this reaction is on that handout. You can see, and one thing you might want to write down is below that is NO2 is brown. You won't necessarily see that in this slide, but that'll come up later. And N2O4 is a colorless gas. So I may try and write this. This is not the best thing at writing. So we're going to say this is brown. And this is, I'll just write clear. So the second gas is clear. Now you can see at the very beginning we have all, if you look at each of these particles, it's the red represents oxygen, the blue represents nitrogen, so all those are NO2 molecules. Here we have a little bit more of a mixture. There are some N2O4 molecules. You see a couple of those there. I would consider these next ones as reaching equilibrium because if you count the number of N2O4, we have 1, 2, 3 of those there. And over here we have the same number. We have 1, 2, 3 of those there. So the number of N2O4 is constant, and also the number of NO2s is constant as well. We have 1, 2, 3, 4, 1, 2, 3, 4. So I would consider C and B at equilibrium because the amounts are not changing. Now you may think, well, everything stopped. Equilibrium is a dynamic process. So those reactants are still changing to products. The products are still changing to reactants. It's just occurring at the same rate. Let's look at the next slide. So here we see the same reaction, but what we see here, they've actually written it in reverse. So what I might direct you to is the third bullet where it says, what do you do if we see a reaction that's written in reverse? Well, actually what you can do is determine the K. The K that's determined is actually the reciprocal of that. So what we're going to be doing with the K is if something is in reciprocal, you just take 1 over that. Now the same thing, if we double all the exponents, you would square the K. If you take 1 over the exponent, so let's say you write the reaction in reverse, then everything's divided by 2, you would do the same thing to the K value. So let's look at, these are the different points that we see. So there's the very beginning where you have the colorless gas. After a point in time you see a little bit of the brown molecules appear, and then we have NO2, which is a little bit darker. Then at the very end you have both. So the next slide we'd like to look at is going back to what we started with. So how would you write a K for this reaction? Now in this reaction we usually have the brown material here, and then we have the colorless gas here. So how do you write a K for this? For this, a K is going to be written, K is always written with products over reactants. So remember with this, when you write a K, the K will be products over reactants. Now, the other thing you have to remember is that your coefficients become exponents. Now, the products have no exponents. There's not a number here, but the reactants do. They have a 2 there. So we're going to have to put a 2 there for a reactant. So if I wrote a K expression for this, it would look simply brackets meaning concentration of N2O4 over the reactants, concentration of NO2, which is squared because there's a 2 in front of that. And let's go to the next slide. So the changes in concentration with time for this is a reaction of water and carbon monoxide going to hydrogen and carbon dioxide. Now one thing I'd like you to notice here is this is a little bit different from the graph that I put on your note sheet. On the one in the note sheet I have reaction on the y-axis, here we have concentration. So an important thing to notice about what is equal at equilibrium, the concentrations, notice they're not the same number, but notice the concentrations do not change, it's a straight line. So a couple things about equilibrium. At equilibrium what is equal are the rates. The concentration is changing the same over the amount of time for each one of these but the concentration is constant. So what happens, the reactants, which are the carbon monoxide and the water, are forming the product CO2 and hydrogen gas, but at some point the rate of the amounts of the reactants are constant, the amounts of the products are constant. Now the position of these two lines depend on temperature. So K is specific to a reaction, but it's also specific to a temperature for that reaction. So let's look at another scenario. In this one, we have the reaction of nitrogen and hydrogen forming ammonia. This is a classical equilibrium reaction. So when only you have nitrogen and hydrogen reacted initially, notice these are the two reactants. Those reduce in amounts, and all of a sudden you see NH3 forming at the same time. Those are disappearing. Notice once in this, again, this goes back to kinetics, the rate of formation and the slopes for each of these lines is not equivalent, because we have different coefficients here. You have a 1, a 3, and a 2. So the slopes of these lines are never the same. But we see they do reach equilibrium at some point because the concentrations will become constant. And so at equilibrium we see the concentrations are constant. They are not equal, but what is equal are the rates, because the reactants are forming the products. The nitrogen and hydrogen are forming ammonia at the same rate at which ammonia is forming nitrogen and hydrogen. So let's look at more and more reaction. This one is like the one on your sheet. Notice this says reaction rates. This is the only time we know for sure that the two lines will meet. We have the forward reaction and the reverse reaction. At some point those two meet, and when those two rates are equal, when the forward rate is equal to the reverse rate, we are at a state of equilibrium. So if you were to observe a system in equilibrium, you cannot tell any difference, because you're not forming more products, you're not forming more reactants. The amounts of reactants and products stay the same, but they're still converting at the same rate. Now we see here, one thing I would change about this is, notice this is a one-way arrow. For equilibrium we represent it with a two-way arrow. So an arrow going to the reactants and an arrow going to the products. Now another thing you could point, we've been talking about reactions here, you could also have equilibrium for a process. For example, you could talk about water as a solid melts and becomes water as a liquid. But if you're holding this at a state of equilibrium, right at that melting point, and the amounts of those are the same, and water is melting at the same rate it's freezing, you hold it exactly there, that is equilibrium. Now, there's not a push to go forward or reverse, so the delta G for that would be 0. So there's not a push to go in either direction. So let's look at another situation. This is a molecular representation of this when you have water and carbon monoxide reacted to form carbon dioxide and hydrogen. You see the first two blocks, we see the water molecules, so you see several water molecules, 1, 2, 3, 4, 5, 6, 7 water molecules. And then we have carbon dioxide as well, 1, 2, 3, 4, 5, 6, 7. So equal molar amounts, and they mention that up here, equal numbers begin to react. Then at some point they reach equilibrium. Now how do you graphically or molecularly represent what equilibrium is? Well, what you do is you want to count the particles. Now notice here, let's go, we see they form hydrogen, so this is a hydrogen particle. So we have 1, 2, 3, 4, 5. So 5 hydrogen gases there. So 1, 2, 3, 4, 5. That would indicate equilibrium. I would expect the same amounts of the other substances. The carbon dioxide, I have 1, 2, 3, 4, 5. And then I have 1, 2, 3, 4, 5 the carbon dioxide. But notice there's still a little bit of reactants. We see a couple of waters, 2 waters, 2 waters. And there's also the other reactant, which was the carbon monoxide. There's also carbon monoxide present. And there's 2 of those on each side as well. So equilibrium would be at these 2 blocks because we have equal numbers of products, and the concentrations of those, when I say equal number of products, it'd be best to be stated that we have equal amounts of the substances each time that we're representing or counting them. So what that's telling us is the concentrations of each substance in that is remaining constant. Let's look at another situation here. So equilibrium is a condition in which the concentrations of all reactants and products in a closed system cease to change with time. So at equilibrium, the rate of the forward is equal to the rate of the reverse. So no further net change is observed. So it looks exactly the same. So whatever you form in the forward is balanced out by what it changes to in the reverse. The amounts of the reactions and products are constant, but they are not necessarily equal. They could be, but that would be not a very typical situation. Let's look at 3 different scenarios for the classical reaction of nitrogen and hydrogen forming ammonia. In the first one, we have all reactants. We have nitrogen and hydrogen. Those are our initial conditions. Those are allowed to reach equilibrium, and we end up with different amounts of nitrogen, hydrogen, and also now ammonia. When we plug these into our equilibrium expression, notice in our equilibrium expression we took our product, which is ammonia, and squared it because it's squared in the reaction, times, and that's over nitrogen, concentration of nitrogen, times the concentration of hydrogen, and hydrogen's cubed because it's cubed in the reaction. Now if we take these values and insert those into our K expression, we end up with this constant, or our K value. Notice this is a capital K. There are no units on K. Now we can start with another situation. In this one we have all products, no reactants. Those products can decompose and form the nitrogen, hydrogen, and you end up with these concentrations. Notice they're not exactly the same concentrations we had before. We plug these concentrations again into our K expression, and we still get the same number. That's because K is a constant. All three experiments were performed at exactly the same temperature. Then we take the third scenario. We have all different concentrations, and then we end up with another set of concentrations when they're allowed to reach equilibrium. Plug these values into our K expression, and once again we have the same constant. This is a constant. The only thing that changes K is temperature. It doesn't matter what initial concentrations we start with. They're going to reach equilibrium, and they will have a constant value of K. So remember, K is a concentration of products raised to the power of the coefficients over the concentration of reactants raised to the power of the coefficients. And the rate of the forward is equal to the rate of the reverse. Now notice the values of M and N are the coefficients in the balanced equation. I mentioned this under 3.2 in the note sheet. In the law of mass action, I've got AA plus VB gives PP plus QQ. Each one of those, if you were to write an equilibrium expression, each one of those coefficients would become exponents. The rates of the forward and reverse reactions are what is equal. The concentrations are not equal. Now, a couple important things. I keep emphasizing this. K is dependent only on the temperature. So temperature is what it's dependent on. Now notice, and you're going to see as we start doing these, anytime you write a K expression, now we have several states of matter. We have solid, liquid, gas, and aqueous. Now, of these four states, two of these can never appear in an equilibrium expression. Those are solid and liquids. We only want to put things in there where we can represent amounts, and amounts as in a concentration. Aqueous would represent amount as in a molarity. Now, gases we can include, because when we talk about a gas, if we have the pressure of the gas, the higher the pressure, the higher concentration. So we can equate pressure and concentration the same, and each one of those can be used. The difference is when we use concentration, we call that a Kc. When we use pressure, we call that a Kp. They're both K values that give us the same indication of which way the reaction proceeds. So if we write the equilibrium expression for this, notice we say concentration of nitrogen dioxide squared over the concentration of our colorless gas, dinitrogen tetroxide, on the bottom. So what I'd like you to do is write the equilibrium constant or the expression for the combustion of propane gas. So what is the first thing you have to do? Notice there are no solids or liquids in this, so everything should be included in the reaction. The first thing you should do is balance that reaction. So do that, and then write your K expression. You can stop this recording if you'd like to while you're doing that. So if you balance the reaction, hopefully this is what you came up with, a balanced reaction. And hopefully that was a final number unit. If you notice that for one of the reactants, the propane, C3H8, I put a 1, but you can actually leave that out of there. So notice the carbon dioxide cubed times the concentration of water to the fourth, and all that's divided by the concentration of propane times the concentration of oxygen to the fifth. So the subscripts, which are C, the Kc indicates concentrations. The value K is usually shown as a unitless number, but it actually does have a unit expression. We just usually don't use those. So the range of equilibrium constant. So a K value, what does that number mean? Well, let's say you have a really, really small K. Small k means you have mostly reactants. Now that's represented in this illustration because the blue dots represent reactants, the red dots represent products. Notice we have almost all reactants there. So you're going to have a small k. Now what does small mean? It means it's going to be a negative number. So if you divide a big number, one number by a bigger number, it should give you a negative exponent. And then we have a large K. Now notice here, this is represented, I believe these are green. And if you have a lot of green particles there, which are products, and very few reactants, that would be a really large K. So this is going to be a huge exponent. And then most Ks are somewhere in between, which are intermediate. So large will be like 10 to the 30th. Negative will be like 10 to the negative 12th. Or, those are just examples. So let's look at two different reactions. We have a reaction that's a mixture of nitrogen and oxygen react to form a very small extent to produce nitrogen monoxide at equilibrium. Notice this is a small K, 10 to the minus 30, extremely small K. Then we have another reaction mixture here, nitrogen and hydrogen forming ammonia, but this goes to 10 to the 8th. That's a rather large K. So this right at K at the top, we think of as small, and this one at the bottom, we think of this as a large K. Okay, so that would be a difference between a large K and a big K. And last, well, how do you write the K? And we've mentioned this several times. Equilibrium constant in terms of pressure. So you can do this and you can just write pressures instead of concentrations. So once again, it's written the same way. The products go on the top and the reactants go on the bottom. Now, notice this is the pressure of gas P to the P, pressure of gas Q to the Q, and this would be pressure of A to the A, pressure of B to the B. But once again, remember, these are your products, and at the bottom we have our reactants. So products over reactants. And so Kp is when you're using equilibrium pressure. Now that usually those will be atmospheres. So the relationship between Kp and Kc, and this will be the last thing we'll cover for today. And this is actually covered under bullet 13.3, so please write down this formula. So this is how do you go back and forth between Kp and Kc. This is how you do it. Kp is equal to Kc times RT to the delta N. Now let's talk about how you do this. I think everybody, Kp and Kc will have no units. R, what units do we want to use for R? We're going to use 0.0821 liters ATM, okay, will be our R value. T will be temperature, and what will be the units of temperature? Please, hopefully you're saying Kelvin. And then NT means change in moles of gas. Now, what in the world's that? Delta N is the moles of gas products minus moles of gas reactants. Now, how do you do that? Let's look at this example, and this is our last slide. Let's say you want to do the delta N for this reaction of nitrogen plus hydrogen forming ammonia. So what you do for this, you'd say moles of gaseous products, these are your products, minus moles of gaseous reactants. These are your reactants. So basically it's going to be 2 minus 4, because you're going to add these two exponents together, gives you minus 2. And so that is a number that you would plug into that expression when you solve for it. So this is where we stop. Hopefully you took some good notes on this, because we're going to jump in and do a lot of equilibrium tomorrow. We have some time to make up for those snow days. Welcome back.